we start it? Action. Okay. So where were we?
Talking about why is it meh?
Why is it meh? They sort of react, but they don't really react over much compared to these elements and these first two groups and the halogens over here. The last group over here, the noble gases, they don't react. They're inert.
They stay the same.
They're unreactive. Why do they stay the same? That's what I want to know.
Because they're already balanced.
They're already balanced.
Not what's the word I'm looking for? Stable.
They're already stable. That's right. Yeah, they're already stable. They have a full valence electron.
What? So the meh ones, they don't they don't easily give up electrons or take electrons as easily as per se like the green and the blue.
That's right. They don't give. These don't give or get anything.
Yeah.
They're stable. They don't want to mess around with anything. It's wrong to say they don't want. Let me rephrase that. They're most stable, so they're unlikely to ever go anywhere else. They're unlikely to take any electrons. They're unlikely to give any electrons.
This one, no, right? This is not.
So stable.
This is
Okay.
No, different.
So that explains
Both very reactive.
Wait, question.
reactivity.
So is that all we have to know?
Wait.
The two groups and the definition and the trend?
And I would know what that chart.
Oh, and explain the graph.
The graph. I'd know how to explain that graph.
Which one? This is the reactive graph?
Yeah, the one with the. Oh wait, I don't know how to explain that graph.
Oh, this thing right here.
Yes.
Oh, we have these and these, and it goes like this.
Yes. I know that little hump is like.
It's something. It's a hump is something. Here we go. Energy, and then we got reaction product products. Right? This is a sloppy diagram.
So at the top, it has a lot of energy, like meaning it's unstable, right?
This is a neutral atom, which we normally think of as very stable, right?
Yeah.
We think of that as like the best way to go. But it turns out that these elements are so reactive that this is more energetic, less stable than if it gives away an electron. Can you believe that? It's crazy. So if you just put in a little bit of energy, put in some energy, put it in, it excites these elements in this row and in that row. I'm just going to say the first group right here, and it gives up an electron. Okay? The amount of energy it takes to do that is the ionization energy. Right?
But this,
as you go down the periodic table, it gets easier and easier to ionize an atom. Why? Because the atom gets bigger. The atom gets bigger and bigger.
And you want it to be stable.
And bigger. And it gets easier to pluck that outside electron away from the atom. So since it's getting bigger and bigger and bigger and bigger, there's less of an attraction to the nucleus. So it's easier just to take that outside electron away. So you just need to bump it, just go like that. This electron will go flying away.
Okay, so the further away it is from the nucleus, the easier it is to get rid of it.
Yes.
But then where does it go?
Where does it go? Well, that's a great question. In the reaction we saw the other day, this electron goes to hydrogen.
Probably than that.
Oh, on Friday. Yeah, we had a big boom. In fact, Mr. Gurney, I think, was...
I never understand the big boom thing.
The big boom?
Big boom thing in class.
Yeah.
So you did that on Friday?
That's what we did on Friday. We just showed different elements reacting. So this is a curve. Let's just say that this is a curve for... How do we say it in class? We said that this is a big curve. Let's say this is for... I don't know.
Oh, you said
sodium. I'm going to say this is sodium's curve. Would lithium's curve be bigger or smaller?
Smaller.
Lithium's curve be bigger or smaller than this? This is sodium. I asked, this is kind of a tricky question. Would lithium have a higher ionization energy or a lower ionization energy?
A lower. Lithium.
We're talking about lithium.
Yeah, it's above it.
We got sodium right here. It's higher, so it's going to have a higher
But how come?
Wait, what?
Wait, no, lithium.
No, it's not.
Lithium has a lower one.
No.
Come on, you almost had it.
Ionization energy increases when it goes down.
What's that?
Ionization energy increases when... No, decreases. Oh, that's
decreases.
here.
Why does it decrease?
Oh, I see. I thought we were looking at this here.
Okay.
Wait, so the ionization decreases as you go down, so it's going to take more energy for... Okay, for lithium.
It takes more energy for lithium to be ionized, meaning that
Yeah,
it
because
takes
the
more.
thing gets bigger.
Because
Right.
it's a smaller radius. No, it's bigger.
It's
It's
exactly-
a bigger radius.
Smaller.
Wait, smaller, smaller.
Second guessing yourself. Okay, so I'm just going to erase this right now.
Everyone.
You guys are all freaking out. Alright, here we go.
There's just
So
so many
that
proportions.
takes the least amount out of
Will
it.
it be greaser?
So you keep on going down.
And that's
Let's
So
do
sodium.
let's do potassium. How about that?
Yeah.
This will be potassium. So it
Which is
takes
even
less energy.
smaller. Even smaller.
Potassium, a little tiny nudge, potassium. Since it's a bigger atom, okay, it's got a
It's got a
lower
bigger
effective nuclear charge.
and a bigger atomic radius, so it's easier to pluck off.
That's right.
And it takes less energy to get the little valence electron.
I still don't see how this has to do with the reaction progress. Like that whole bottom thing. I don't get that.
How do you get from this one to this? This is the start, this is the finish.
Oh, so you
So
use the ionization energy, bump off an electron.
Yes.
And that's how it gets down there.
Yes, that's how it gets stable. As soon as you bump up that electron, it gets so stable because then when it gets that extra electron bumped off, it's got a full valence shell. It looks just
But
like a noble
lithium-
gas.
Because lithium doesn't have one, a full valence.
Oh, but when it gets its electron bumped off, it does.
Oh yeah.
Wait, so the bigger the atom, the easier it is to pluck off electron.
Yeah.
Okay, because there's more shells being added, right?
Yes.
So,
Okay. It's farther away from the nucleus. It feels less of a pull from the nucleus.
I think the thing I really just gotta work on is just like memorizing the trends and memorizing like how like
Yeah.
once I got that down, I think like on the test, on the back I should just draw like a big like periodic table and just like list all the trends
You
and how
can,
they increase.
you can, but the biggest thing to know is this is the effective. If you know the effective nuclear charge, right?
Not everything else.
If you know that trend, you can predict everything else.
Why?
if you know the Zeph,
Yeah, the ZEF. Right? And think about the ZEF, the Z effective, the effective nuclear charge. They're all the same thing. Right? As you're going from left to right on the periodic table, the effective nuclear charge gets bigger. And it does that. Here's the key insight. This is what Andrew was asking about before. This is what he wanted me to answer. As you're going across the periodic table, going this way, across the periodic table, you're adding more protons along the way. Because you go from element to element, just by definition, if you add another proton, you get a new element. Right? You're also adding another electron on. I know you guys are zoning out. It's the end of the day. I
No, I'm
get
just
you.
looking at like the whole flammable thing, like freaking me out.
Hey, keep going. I was paying attention.
Okay.
So
So as you're going across the periodic that's a train of
So
thought.
deep dive.
As you're going across the periodic table, you're adding more protons. You're also adding more electrons. Those electrons are added to the same shell, right? We had a little animation that showed that. You ready? Okay. As you're adding more electrons to that same shell, they're also being pulled in closer and closer and closer to the nucleus. Because
Left to right.
Yes, left to right, because you're adding more electrons about the same distance, and you're getting more and more positive charge in the middle. So as you're adding more positive charge, these electrons are going to be squeezed in closer
They're
and
more
closer and closer.
attracted, so there's more zap.
Attracted. So since they're more attracted, you can predict everything else. It's all about the attraction between the nucleus and its electrons. If you know that, then you can know everything else.
Okay, so then this relates to my question on page 70, number 3, and why is Na a smaller sodium a smaller atom than neon?
And
Okay.
A plus
We're
1.
going to get to that. Okay, we're going to get to that. Page 70, number 3 in a second, but
Okay, on the graph, the part when it's going down, when it's decreasing the line,
yeah.
you know, that's when the element is releasing hydrogen.
No, that is when the element is releasing energy. It can ignite hydrogen.
Ah.
Right?
What is
Wait,
ignite?
ignite hydrogen.
What does ignite mean?
I
Ignite
know
means
it's like fire. Like,
Yeah, but I don't understand this. Hey, what's? Oh my god, your finger.
I
you
know.
see that? Oh, okay.
yeah.
Ignite. What's
It's
ignite?
like to ignite the fire, like
just happened.
when you turn on the stove,
To lit.
when you turn the
To
thing,
lit.
the dial, yeah, to light, like, you know.
Also, it's light from the hydrogen.
we have heard
And
the Katy
release
Perry
energy.
song, they use it.
Releases.
Laugh.
Yeah, but it releases energy
yes.
and
It gives
ignite
What is, I don't
It
get,
is an
hydrogen.
explosion.
why does it
Okay.
You get an
ignite
explosion
hydrogen?
from it. Where is the camera? Okay. So
Okay. Good.
You're good?
Well, why does
All right, we'll
hydrogen-
see you later.
hydrogen-
Now, we've got to talk about how many minutes we got on this?
10.
10 minutes. Okay, we can do this in 4 minutes. That way we can put this online under the limit. Number three. Number 3 gives you a question that is kind of crazy. Right? It says, can you read the question out loud, Sophie?
Yes, I can. Okay. These following elements, which is F, charge of -1, Ne, Na, charge of +1. These elements all have 10 electrons. Which has the highest depth? And which do you think would be the smallest atom and why?
Right. Let's calculate the Z. The Z effective right away. Right. Z effective for fluorine. Okay. It's going to be Z minus S. Fluorine Z. What's fluorine?
Fluorine is
9. Good. 9 minus how many core electrons in fluorine? We got 2. Okay. So the overall is going to be 7. Right. That's fluorine's Z effective.
Oh yeah, it is.
Okay. Neons. What's neon's Z effective?
8.
Let's get
No,
this.
yes, it is.
Z minus S. We've got 10 protons minus number of core electrons,
Core
it'll be 2.
electrons, yeah.
So it's going to be ZF is going to be 8. Yeah. So far, neon has a higher Z effective.
Wait, sorry, I just need to check this out.
Okay. Now let's do sodium. Sodium's the oddball. This is the one similar to the magnesium +2 that we did the other day, or that we did the.
Oh, wait, the -1 charge on fluorine, you didn't do anything.
But according to our formula here, it's just the number of protons minus the number of core electrons. The core electrons did not change. Valence electrons changed. See you later. Valence electrons changed.
Okay.
They changed because you added another electron.
Yes.
But the core did not change.
Okay.
Okay? Okay. Now let's do sodium. Okay. Sodium's a little bit different. So to see this, I'm going to write out its electron configuration normally, and then I'm going to take away an electron. Why am I going to do
Because
that?
it's plus yours to taking away an electron.
There we go. So let's try. 1s2, 2s2,
2.
2p6, 3
That's 1.
S1. Okay. Now, normally, we'd have this as our valence electron, and these would be our core. How did I know that? Because these all are in earlier shells. We've got the second shell here, and first shell right there.
Yes, got it.
It's the third shell.
Yeah.
But it's a little bit crazy now because now we're going to take away an electron. So let's do that. Just took it away. Now how many electrons do we have in the core?
2.
2. Right? So we've got 2 core electrons. Now let's apply this formula, which is Z minus S. Z is, again, the number of protons. So for sodium, it's going to be 11 minus
2.
2. Wow. The Z effective now is 9.
So wait, now you added Na has 11 originally, so you're doing 11 minus, wait, now after for the core electrons you just did 2, so minus 2.
Yeah.
And then the Zeph equals 9.
Yeah.
Okay.
Okay?
Whereas normally, whereas
Yeah.
normally Na, if you didn't have any charge, the core electrons would be 10.
Core electrons would be 10, yes. Normally
Okay.
it would be.
Okay, got it.
But now, since we've taken one away, it